Hi everyone, welcome back to PRAKASAM tutorials. In my previous videos, we have discussed about movement about origin and movement about mean. Now here in this video, I am going to discuss about movement generating function concept. So before going to the movement generating function, briefly I will explain once again the concept of movement about origin and movement about mean. So capital X is a random variable. The nth moment of a random variable capital X is denoted by or represented by expectation of x power n or m suffix n, and the representation of nth moment central moment of a random variable capital X is given by or defined as expectation of x minus m whole to the power of n. Now here movement about the origin in this expectation of x power n, substitute different values of n that are n is equal to 1, n is equal to 2, n is equal to 3, like that. We get first movement of a random variable x, substitute n is equal to 1, we get first movement of a random variable, that is expectation of x, substitute n is equal to 2, we get second movement of a random variable, that is expectation of x square, and similarly the nth central moment of a random variable x in this expression also substitute different values of n that are n is equal to 1, n is equal to 2, like that. Substitute n is equal to 2 in the central moment of the random variable, we get expectation of x minus m whole square. So that expectation of x minus m whole square is the variance of the random variable. Okay, so this mean and variance and other moments gives some useful information about the variance of the uh, some useful information about the random variables. So this is already discussed in previous videos. So now here we are going to discuss about movement generating function. An important device that can be used to calculate the higher movements is the movement generating function. Capital X is the random variable. Capital X is the random variable. The movement generating function of a random variable capital X about the origin, whose probability density function is given by mx of t is equal expectation of e power tx, which is equal to integral minus infinity to infinity e power tx into probability density function dx. So capital X is the movement generating function of a random variable, and this is the probability density function of a movement generating function random variable capital X for continuous case. Here fx of x is the probability density function of a random variable. So about the origin at x is equal to 0. So this is the equation about the origin of the movement generating function definition and movement generating function for continuous random variable. So at x is equal to 0 means that is movement generating function is expectation of e power tx is the about origin. For discrete random variable, the movement generating function of the random variable is given by mx of t is equal expectation of e power tx sigma I is equal to 1 to capital N e power txi into probability of xi. So p of xi is the probability of the random variable x is equal to xi. So this is the definition of the movement generating function of a random variable, and movement generating function of a random variable capital X for a continuous random variable expression, and movement generating function of a random variable for discrete case expression. Here in this expression t is not a time. Here in this expression small t is not a time. It is a variable. Since the moment generating function is used to generate the moments, it is known as moment generating function. Mx of t is used to generate the moments. It is known as moment generating function. So we know that the expansion of e power tx, expansion is e power tx is equal to 1 plus tx by 1 factorial plus tx whole square by 2 factorial plus tx whole cube by 3 factorial plus and so on. So this is the expansion of the e power tx. Now here the definition of the moment generating function is mx of t is equal to expectation of e power tx. So this within the bracket term is applying expansion of e power tx. We get expectation of 1 plus tx by 1 factorial plus t square x square by 2 factorial plus t cube x cube by 3 factorial plus and so on. So on RHS side applying the expectation on each term. So we know that according to properties of expectation, expectation of sum of random variables is equal to sum of their individual expectation. So using that property, the RHS term is written as mx of t is equal to expectation of 1 plus expectation of tx 1 factorial is 1. Expectation of t square x square by 2 factorial plus expectation of t cube x cube by 3 factorial plus and so on. So now here the time small t is not a time. Small t is not a time, but it is a variable. So there is a constant. So expectation of tx. So using the properties of expectation, expectation of ax is a into expectation of x. So using that property, expectation of tx is t into expectation of x. Expectation of t square x square is t square into expectation of x square. So expectation of t cube x cube is t cube into expectation of x cube by 3 factorial plus and so on. Similarly, rth term t power r into expectation of x power r by r factorial plus and so on. So expectation of 1 is 1. Expectation of 1 is 1. So now here in this equation, expectation of x is the first moment of the random variable. Expectation of x square is the second moment of the random variable. Expectation of x cube is the third moment of the random variable. Expectation of x power r is the rth moment of the random variable. So therefore, from this equation, the moment generating function of a random variable is mx of t is equal 1 plus t m1 plus t square by 2 factorial m2 plus t cube by 3 factorial m3 plus and so on t power r by r factorial into m suffix r plus and so on. So now here in this equation, m suffix r is the rth moment of a random variable. For a continuous case, the rth moment of the random variable is m suffix r or expectation of x power r is equal integral x power x f of x dx, and for discrete case the rth moment of a random variable is m suffix r is equal expectation of x power r, which is equal to sigma xi power r into p of xi. M suffix r is the rth moment of the random variable x about the origin. So that is expectation of x power r is equal to m suffix r is the coefficient. So that rth moment of the random variable coefficient is t power r by r factorial in the expansion of the moment generating function in series of powers of t. So in order to find rth moment about the origin, we have to differentiate the moment generating function mx of t with respect to r, with respect to r, with respect to t r times. Once again, in order to determine the rth moment about the origin, we have to differentiate the moment generating function mx of t small r times with respect to t. and substituting t is equal to 0. So using this expression, we calculate the rth moment of a random variable capital X. And what is the definition of the moment generating function of a random variable? Mx of t is equal to expectation of e power tx. That is the definition of the moment generating function of the random variable capital X at the point about origin. About the origin mean at x is equal to 0. Similarly, the moment generating function of a random variable capital X about the point x is equal to a is given by mx of t is equal, so x is equal to a is coming to the LHS side, we have x minus a. So the definition of the moment generating function of the random variable about point a is defined as mx of t is equal expectation of e power t into x minus a.